So let's look at the 2008. We're talking about the depth at Doe River Picnic Point. You know it's 24 feet wide at this location. And the measurements when taking a straight line perpendicular to the edge of the river. The data shown in the table are the measurements, and it's the velocity of the water at Picnic Point in feet per minute, and it's modeled by this function. And this is a calculator active. So A says use a trapezoidal sum with 4 subintervals indicated by the data to approximate the area of the cross section of the river in square feet. Show the computation. So we're going to go 1/2 because that's part of the trapezoid formula. The width of our first rectangle is 8. We're going to use our 2 bases, and then 6, then 8, then 2. And if you do that, you get 115 feet squared. Now, part B says the volume flow at the location is a product of the cross-section area and the velocity of the water at that location. Use your approximation from part A to estimate the average value of the flow from 0 to 120. So what you found in A is the approximation of the area. So average is 1B minus A, so that's 1 over 120. You're going from 0 to 120 because it told you that. And you're doing 115 that you found up here times your velocity, because that's what it says. It's the cross-section, the product of the cross-section area and the velocity. You can use Math 9, and you get 1807.170 feet cubed per minute. So remember, volume is always going to be cubed. Now, part C is a scientist proposes the function given by f of x as a model for the depth of the water at Picnic Point. X feet from river's edge. Now, how far did they tell you? It's 24 feet, right? So find the area of the cross-section of the river on this model. So we're going from 0 to 24 because that's the width of the river. And we're going to do f of x, d of x, because it says that this is the model for the depth in feet. And you use a Math 9 and you get 122.23 feet squared. So part D says recall that the flow is a product of the cross-section area and the velocity. To prevent flooding, water must be diverted if the average value exceeds 2,100 cubic feet. Use your answer from part C as the average to find the average value of the flow during the time interval 40 to 60. Does the value indicate that the water must be diverted? So average value is 1 minus B minus A. We're going from 40 to 60. We're going to use the average value here times the velocity, because they said the cross-section area, remember, product velocity, and 2.181.89. And so does it need to be diverted? Yes, it does, because it exceeds 2,100. So we're going to look at the next one. It's the 2007. This is a non-calculator. The table of values is talking about how the volume of the hot air balloon expands, and the radius of the balloon is modeled by this function. T is measured in minutes. It tells you that the graph is concave down, and it gives you selected values of the rate of change. So this is the rate of change of the radius. And it tells you the volume of a sphere, and it gives you that formula. So it says estimate the radius of the balloon when t equal 5.5 using the tangent line approximation at t equal 5. Is your estimate greater than or less than the true value? Okay, so tangent line means you're going to get a tangent line and then you're going to plug 5.4 in. So at t equal 5, we know the slope is what? 2, because that came straight from our table. And it tells you that the radius of balloon is 30 feet when t equal 5. So we've got our ordered pair. We plug in and get our B. And then we plug in 5.4, work it out, get 30.8. Now, it told us that it's concave down. So think about your drawing. If your curve is concave down, your tangent line's sitting on top. So it's going to be an over approximation. All right, so part B says find the rate of change of the volume of the balloon with respect to time, t equal 5, indicate units. So this is where your related rates. So they gave you the formula. You're going to say dv dt. You're going to do your derivative power rule. So you're going to 4 pi r squared dr dt. And then you're going to plug in, you know your radius is 30 at 5. And we already said that the slope was 2. And if you work all that out, you get 7,200 pi feet cubed per minute. That's how the volume is changing. And part C says use a right Riemann sum with 5 subintervals to approximate 0 to 12 and explain the meaning. So you're doing 5 subintervals, so you got 1, 2, 3, 4, 5. By now, I hope you know, so the difference in the x's is the width, and then you're doing right, so you take your right order pair, and you add them all up, and you get 19.3 feet. And it won't explain the meaning of that in terms of the radius of the balloon. So that's the rate of change of the radius, how much it's changed from 0 to 12 seconds. The radius is increased by 19.3 feet from 0 to 12 minutes. And D is your approximation in part C, greater than or less than 0 to 12. Give a reason for your answer. So it's a decreasing function. So if it's a decreasing function, think how that looks. Your right value will be an under approximation of the actual, if you had a function rule to get the derivative. So our next one's a 2006. It's a non-calculator. They give you a table of values about rocket A's velocity from an initial height of 0, and it's going from 0 to 80 seconds. So it says find the average acceleration over the time interval 0 to 80. Indicate. So you're finding the average acceleration. Well, acceleration is the derivative of velocity. So you're going to take your slope formula, v of 80, and you're going to work it out, and you're going to get 0.55 feet per second squared. So remember, acceleration is a rate of change, so you say average rate of change. That's what that is. And part B says use correct units to explain 10 to 70 v of t in terms of the rocket flight. Use a midpoint Riemann sum with 3 subintervals. So remember, you're going from 10 to 70. So your width is going to be 20, because 70 minus 10 is 60 divided by 3. So your first one's going to be here, your second one from here to here, and your third one. So wait a minute, I did that. So you're going to go 10 to 30, 30 to 50, and then 50 to 70. So notice where your midpoint's going to fall in between each of those. So you know it's an even width of 20, and so you just do the midpoint of each of those intervals and add them up, and you get 2,020 feet. And that's the distance in feet that the rocket traveled from 10 to 70 seconds. Now, part C says rocket B is launched upward with an acceleration of a of t equal 3 over the square root of t plus 1. The initial height is 0, and the initial velocity is 2 feet per second. Which two rockets is traveling faster at t equal 80 seconds? So we have velocity 80 for rocket A, but rocket B, we're going to have to do an integral to get our velocity function. So we're going to do the integral of the acceleration, square root of t plus 1. Now we got to use u substitution. So use t plus 1, d use dt. I'm going to pull my 3 out, make it u be negative 1/2. And so when I do my power integral rule, I'm going to get 6 u half 1/2 plus c. I'm going to plug that in for my new for my U. And now I'm going to solve for C because it said velocity is 2 feet per second on the initial. So when time is 0, velocity is 2. So if you work that out, C equals -4. So you can go back and say the rocket function is 6t plus 1 minus 4. You plug 80 in and you get 50 feet. So rocket A had 49 feet. So rocket B is traveling faster because 50 is greater than 49. So again, this is a non-calculator one, the 2006. They give you a table of values of velocity and acceleration about a car traveling. And it says they're continuous functions. So it says explain the medium at 30 to 60, absolute value of V of t, and approximate using a trapezoid approximation with 3 subintervals. So the absolute value of velocity in an integral is the total distance traveled. And if we're going to do 3 subintervals, they're going to be, so it did say 3, yeah. And we're going from 30 to 60, so be careful, you're going from 30 to 60. So you got this one, and this one. You're not doing the whole thing. So if you do a trapezoid, you got 1/2, and then the width of the first one is 5. And remember, you're doing absolute value. So when you come in here and do your base, -14, -10, you're doing the absolute value of it. And then the next width is 15, absolute value of your 2 bases, and 10, absolute value of your 2 bases. And if you work all that out, you get 185 feet. And again, that's the total distance traveled from 30 to 60 seconds. Now, Part B says, explain the meaning of 0 to 30, A of t, find the value. So, A of t is the change in velocity from 0 to 30. And we're going to go 0 to 30, A of t is the same thing as 0 to 30 of the derivative of v, because acceleration is velocity derivative. And remember, if you take the integral of derivative, it's just v of 30 minus v of 0. And you can pull that from your table, and you're going to get 6 feet per second. Part C says, from 0 to 60 must there be a time where v of t equal -5. So, you can use intermediate value theorem, because remember, if you've got a continuous function and you've got an interval where your value falls between f of b minus f of a, then intermediate value says it'll apply. So if I look at 35 to 50, look right here, 35 to 50, -5 is between velocity of 35 and velocity of 50. So the intermediate value theorem guarantees that it's going to cross -5 because it goes from -10 to 0 in a continuous function. Now part B, 0 to 60, must there be a time where A of t equals 0. So here we're going to use our mean value theorem. Now mean value theorem, remember, says there's the derivative is equal to f of b minus f of a over b minus a. So you want it to be 0. So think where f of b and f of a would be the same, because then your numerator would be 0. So if you look at 0 and 25, look up here, 0 and 25, see how they're both -20? So if I do v of 25 minus v of 0, I'm going to get 0. So the mean value theorem says there has to be a time where you take the derivative that will equal 0.